everyone. In this video, we're going to talk about section 3.5, which is about the hypergeometric and negative binomial distributions. So in this chapter, we're introducing two new distributions that are like the binomial, but address different situations. So both of these distributions are related in some way to the binomial distribution. The hypergeometric is very much similar to the binomial, except we now know the population and sample sizes. So before in the binomial distribution, we knew the sample size, but we didn't in fact know the entire population size. So we know there's like a sample of size whatever from a possibly infinite population. In the hypergeometric distribution, or in the situation where we would use a hypergeometric distribution, we know the population and we know the sample size, both sample sizes, both population size and sample size. For the negative binomial distribution, instead of looking at the number of successes out of n trials, we are looking for essentially how many failures until a certain success. So instead of looking at how many successes out of n trials, we're looking at the number of failures until the rth success is what we'll do there. And so that's what we're saying. That's what I'm trying to say in that sentence right there. Okay. Now we're going to start with the hypergeometric distribution and its assumptions. So the assumptions there are that we know that the population or set to be sampled from consists of capital N individuals, objects, or elements. So capital N things are what we have in the population. There are only two possible outcomes, just like the binomial distribution, success or failure, and there are a fixed number of successes in the population. So not only do we know the population size, N, capital N, we also know how many successes or types of a certain thing are in the population as well, so capital M. And third, we have a sample of little n individuals are selected without replacement in such a way that each subset is equally likely to be chosen. Okay, so we've got n individuals, objects, or elements that are selected without replacement, and we know that each subset of size n is equally likely to be chosen. That's not really the important part of what we need to worry about there, but it is the third assumption. Here's where we show the actual distribution. So the hypergeometric random variable, so a random variable that's assessing a hypergeometric situation or experiment, is going to be counting the number of successes in the sample. Right? So remember, we have a population of size n, and we have a number of successes that we know is in the population, size m. We take a sample of size little n, and here x is counting the number of successes in the sample, not in the population. So there's a lot of things running around here that we have to keep track of. The three parameters of the hypergeometric distribution are the three of the things that can change. One, the sample size. Okay, so little n can change. Capital N can change different populations, and then capital M can change number of successes in the population. Given those three things, we're going to denote a random variable that has a hypergeometric distribution, like so. Remember, the tilde represents or says in words is distributed as. So here x is distributed as hypergeometric with a sample size of little n, number of successes in the population, capital M, and then population size n. Okay, here's the PMF. Okay, and it's interesting. Again, we've got a number of chooses here. So we've got m choose x times n minus m choose n minus x, okay, over capital N choose little n. And again, they all sort of have a significance that we can talk about or try to reason through why the PMF looks like this. Remember, capital M is the number of successes in the population. So this is number of ways that I could choose X, number of successes in the sample from M in the population. So that first choose talks about the successes. The second one talks about the failures, right? Capital N minus capital M, that's the number of failures in the population. Choose little n minus little x, which is the number of failures in the sample, over the sample and population sizes. So that's how many ways are there to choose little n from big N. So how many samples of size how many samples of size n, little n, can I choose from a population size of capital N? All right, so if none of that made sense, it's totally fine. There's a formula. We can use it. But the important part here is that there are some restrictions on x of what we can put into this function. And there were also restrictions on x from the binomial standpoint in our last distribution that we talked about. X couldn't be larger than the sample size. So that time, x had to be between 0 and n. Okay. This time, we've got some more interesting bounds. X has to be between the maximum of 0 and n minus n plus m. And it can be between that and the minimum of n and m. And so each of these also has a use or comes from a certain place. If there are the right-hand side, this side, it talks about, it's a sort of restriction on successes. So in fact, if I take a sample of size 10, and there is in fact only 9 successes in the population, so if n was bigger than m, then in the sample, I can only have up to m successes. If my sample is larger than the number of successes in the population, then it's a fact that there has to be at least a couple of failures in there. Because if I've taken all the successes away in the population and then my sample is larger than that, then there has to be some failures in there. And so that's where the top of it comes from. And the bottom of it comes from the sort of failures part of it. It's a little more nuanced to talk about, but you can look in the book. It has a nice description of why those bounds are the way they are. Again, it's not super important that we understand exactly why those are there. I just have to be thorough when I write this down, just for my own saneness. Okay. So let's do an example. And I'm not even going to begin to write down the PMF here and try to solve it by hand. We're going to go right to Minitab from now on. Okay. Although it's important still to know where the probabilities are coming from, we're going to let the computer do all the work for us. So here's an example. It's taken from the book. During a particular period in the university's information technology office, they received 20 service orders for problems with printers, okay, of which 8 were laser printers, 12 were inkjet printers. Okay. A sample, so as we go, let's write down the sort of important parts here. There were, in the population, there were 20 service orders for printers. capital N is 20. All right. 8 were laser, 12 inkjet. A sample of size 5 of these service orders were selected to be A sample of size 5 of these service orders is to be selected for inclusion in a customer satisfaction survey. Okay. Suppose that 5 are selected in a completely random fashion so that any particular subset of size 5 has the same chance of being selected as does the other subject. Okay, great. So we're taking capital N, 20 in the population, little n, sample of size 5. In that last part that I read, they made sure to include that so that this would be a hypergeometric situation. Every subset of size 5 has the same chances being selected, so on and so forth. Okay. It says, what's the probability that exactly x, where x is 0, 1, 2, 3, 4, or 5, of the selected service orders were for inkjet printers? Okay, so it's in the book they go through and calculate all of them, and certainly we can do that too, but I might choose one single one. So let's say instead of all of these, we'll just say that like 3 of those were for inkjet printers, right? And so we're specifically interested in inkjet, and so the reason why I haven't written down M yet is I needed to know what was a success and what was a failure. And so here a success is inkjet, a failure is laser. And so M, in the population, there were 12 inkjet printers. And so I want to find the probability that 3 of the 5 that were sampled were inkjet printers. Okay? And so there's X, N, N, and M. And if I wanted to, I, of course, could write down the PMF, F of 3, okay, given capital N was 20, capital M was 12, and little n is 5. It's a lot of chooses, so it's 12 choose 3 times 8 choose 2 over 20 choose 5. And so you'd have to do all the chooses, multiply together, all that good stuff. So, okay, we've got the binomial stuff here from last videos, but we're going to go to calculate probability distributions, probability density, and we want to find hypergeometric here, which is hypergeometric. The value is 3, population size. They have nice N, M, and N to make sure that you know which one. Population size is 20. Count in the population is 12. Sample size is 5. So we click OK. And then there is our hypergeometric probability. For 3, the probability that X is 3 is 39.7%. 39.7%. Okay? And of course, you could answer any sort of cumulative probability with ease with Minitab. And so, in fact, that's what I'm going to ask you to do. Your turn. You have another situation, and I want you to find the following probabilities. Hardest part of this, your turn, is going to be picking out what is capital N, what is capital M, and then little n.